Welcome to AI Paper Podcasts, where we break down complex AI research into, well, something you can actually use.
That's the goal.
Today, we're tackling a really common headache with large language models.
Oh.
They often seem to hit a wall, They learn, they improve, but then they just get stuck.
Right. They settle into what's called a local optimum. Good answers, maybe, but not the best answers, and they stop exploring, stop innovating. Progress just kind of fizzles out.
But what if there was a way, maybe even an elegant way, to nudge them past that point, to unlock continuous improvement?
Well, that's exactly what we're digging into today. There's this fantastic paper, Pass at K Training for Adaptively Balancing Exploration and Exploitation of Large Reasoning Models. It's by Ziping Chen and colleagues from Renmin University of China and ByteDance Seed.
Okay, so let's get straight to the core insight for everyone listening, especially for that quick summary. This paper shows that a seemingly small tweak, changing the reward metric in reinforcement learning from pass at 1 to pass at K, can fundamentally change how LLMs learn.
It rebalances that critical trade-off between exploring new possibilities and exploiting what the model already knows.
And the really surprising part, the kicker. This method lets smaller models, we're talking 7 billion parameter models, actually outperform giants like GPT-4o and Claude 3.7 on some tough reasoning tasks.
It's pretty remarkable. It suggests there's untapped potential even in smaller models if we train them smarter.
So our mission today is to really unpack how this pass at K training works its magic. We'll get into the mechanics, the why behind it, giving you those aha moments to help you stay ahead in AI research.
Let's dive in.
All right, let's set the stage. The problem. Getting these LLMs unstuck. We're operating in the realm of reinforcement learning with verifiable rewards, or RLVR.
RLVR is a super powerful technique. It's how many top models learn complex reasoning. The model tries something, generates a response,
and gets a reward if it's right, based on verifiable correctness, like solving a math problem or passing a unit test in code generation. Think models like OpenAI's O1 RLVR is key there.
Exactly. But the standard way, the tradition, has a catch. It usually relies on pass at 1 for that reward.
Okay, let's break down pass at 1.
Right.
What does that actually mean in practice?
It means the model only gets that positive reward, that pat on the back, if its very, very first attempt is correct.
Only the first one? Wow.
Yep. If it messes up the first try but nails it on the second or third, tough luck. That first failure gets 0 positive reinforcement.
That sounds incredibly strict. And it brings up this fundamental idea in AI exploration versus exploitation.
The eternal balancing act. Exploration is the model trying new things, being adventurous, generating diverse ideas, even if they might fail.
Venturing out, yeah. And exploitation is sticking to what works.
Pretty much. Refining known strategies using reliable actions that have succeeded before. Playing it safe, essentially.
So the big problem with pass at 1 training is it pushes way too hard towards exploitation. Makes the models too safe.
Precisely. It makes them overly cautious. Think about like a chef. Imagine they only get paid if the absolute first dish they try making is perfect.
They'd never experiment. They'd just make the same foolproof dish over and over again.
Exactly. Even if their failed experiments, their slightly burnt soufflés, contain useful lessons or parts of a brilliant new idea, they get no reward, so why risk it?
So the LLM, under pass at 1, just keeps generating the same kinds of safe answers, because those are the ones most likely to maybe hit the mark on the first try. It converges to that local optimum.
It gets trapped. It's like that chef making decent spaghetti carbonara forever, never discovering their potential for molecular gastronomy because the risk of failure on try number 1 is too high.
The model's true potential remains locked away.
And that's the rut traditional RLVR methods often struggle to get models out of.
Okay, this is where the paper flips the script. And honestly, this is where it gets really exciting. Their core idea, switch from pass at 1 to pass at K.
Deceptively simple, right? But profound.
So instead of needing the first answer to be right, the model gets a reward if at least 1 out of K attempts is correct. K could be, say, 4 or 8 or 16 attempts.
It completely reframes the goal. It's a fundamental shift in the incentive structure.
And the impact is immediate.
Oh, yeah. Instead of just aiming for that single perfect shot, the model is now encouraged, even incentivized, to generate a whole suite of candidate solutions for each problem.
Like trying different angles on the same problem.
Exactly. And naturally, those solutions start covering different parts of the solution space. They become more diverse, less conservative. The paper puts it nicely. The stronger exploration ability enables the model to acquire more comprehensive knowledge and stronger robustness.
Robustness.
Yeah.
That's key for real-world use, right? So for you listening, this means the model isn't just good on its training data, but less likely to break unexpectedly when it sees slightly different problems.
That's the idea. More resilient, more reliable.
And they have data to back this up. You mentioned charts.
They do. If you look at the results, like in Figure 3, you see pass at K training, often shown as light blue triangles, just keeps climbing. In pass at K performance, it doesn't stall.
While the pass at 1 training, the purple dots, hits that ceiling we talked about, that local optimum.
Right, it flatlines. It's a clear visual difference. Pass at K keeps the learning going. It stops the model getting stuck.
And importantly, does this hurt the pass at 1 score? Like, does it become less accurate on its first try because it's exploring more?
That's the fascinating part. No, not really. The paper shows it significantly enhances pass at K performance while not harming pass at 1 scores. In fact, as we'll see later, it often ends up boosting pass at 1 performance down the line.
So better exploration actually helps exploitation later.
It seems so. They're not necessarily enemies.
Okay, but generating K responses for every single step sounds computationally expensive. Is there a catch?
Well, the naive way, what they call full sampling, can be. That's where you generate, say, n responses and rigidly divide them into n distinct groups. That involves generating a lot of responses up front.
Yeah, lots of GPU time.
So they came up with some clever enhancements. The first one is bootstrap sampling.
Bootstrap, like pulling yourself up by your bootstraps, or more like the statistical technique.
More like the statistical technique. Instead of rigid groups, you have a pool of responses, say n rollout responses, and you randomly sample k of them to form each training group.
Ah, so a single response could end up in multiple sampled groups.
Exactly, that's the key. It turns out you don't need strictly separate groups. This random sampling approach lets you use fewer total rollouts. N rollout can be smaller than what full sampling needs, while still forming the same number of training groups.
Which means less computation, faster training.
Bingo! Higher training efficiency. More bang for your compute buck. Their Figure 4 shows bootstrap sampling, the dark purple line clearly beating full sampling, the light green line with the same number of total rollout.
Smarter sampling, basically. But they didn't stop there, right? There's something about an analytical derivation.
Yes, and this is where it gets really elegant, I think. Instead of relying on sampling to estimate how good or bad each response was relative to the others in its group.
Which would introduce noise, randomness.
Right. They derived mathematical formulas, analytical solutions for the advantage values of the positive, correct, and negative incorrect responses within a pass at K framework.
Advantage values. That's like the model's internal score, telling it how much better an action was than its average action.
Essentially, yes. By calculating it directly with a formula, they remove the variance brought by the sampling operation.
Okay, removing variance, why is that so important?
Think of training stability. Variance is like trying to aim at a target that's constantly jittering around because of random sampling noise.
This is hard to hit consistently.
Very. By using the analytical derivation, they lock the target in place. It gives a much smoother, more stable training signal. The paper notes it leads to a more stable training process and continuous performance improvements.
And this shows up in the results too.
Absolutely. Look at Figure 5. Pass a K training with this analytical derivation, the red line just walks away from both bootstrap sampling and standard pass at 1 training. Higher accuracy, more consistent gains over time for both pass at 1 and pass at K metrics.
So for anyone developing these models, this analytical approach offers a more robust, more reliable way to implement pass at K training.
Definitely. It takes out the guesswork and randomness associated with sampling the advantage values.
This does make me wonder though, is pass at K really boosting exploration? Or is it just a different way of calculating rewards that happens to work well? People have tried other things to encourage exploration, right? Like adding noise.
They have. Things like noise rewards, where you randomly flip the reward signal for some incorrect answers, hoping to make the model explore more.
How did that work out?
According to this paper, not well. They found it significantly degrades model performance. Just adding random noise seems too chaotic. It doesn't provide structured guidance.
Okay, what about entropy regularization? Trying to directly push the model to have more diverse outputs.
That's another approach. Entropy is a good measure of diversity or exploration, but directly optimizing for higher entropy can be tricky. The paper mentions it might cause the collapse of the model or lead to trade-off issues. It's hard to get right and doesn't seem to lead to the same continuous improvement.
So pass at K's design, tying the reward to finding at least one correct answer in a batch, seems to be the key differentiator. It's structured exploration.
That seems to be the case. It encourages exploration in a useful direction, guided by the actual task success.
So how do we know it's really exploration that's improving? What's the evidence?
They look at a couple of things. First, answer diversity. They measured how different the answers were, especially when the model failed to find a correct answer, negative responses.
What did they find?
Pass at K training encourages diverse answers when the model is not confident about this question. Which makes sense, right? If you get multiple shots, K1, you're more likely to try different strategies if the first few don't work.
Whereas the pass at one model just keeps trying slightly different versions of its first failed idea.
Pretty much. It generates safer, more similar answers. Figure 7a shows this clearly. The diversity of negative responses, dark purple line, goes up with pass at K training.
Okay, diversity up. What else?
They also looked at the entropy of the policy distribution. That's a measure of how uncertain or diverse the model's internal predictions are.
Higher entropy means more exploration.
Generally, yes. More spread out probabilities over possible next actions. And they found pass at K training keeps the entropy at a relatively high level, while under pass at 1 training, it quickly drops low as the model converges to its safe strategy. Figure 7b shows this divergence.
So more diverse answers, higher internal entropy. It really does seem to boost exploration.
And it leads to this really important insight they mention. Exploration and exploitation aren't always fighting each other. They can mutually enhance each other.
Interesting. Better exploration leads to finding better strategies to exploit.
Exactly. Pass at K seems to find that balance.
Is it finicky? Like, does it only work if you pick the perfect value for K?
Surprisingly robust, actually. They tested K4, 8, and 16 and found it works well across the board. It's robust to different values of K.
That's great news for practitioners. Less hyperparameter tuning help.
Right. They do note that larger K values can sometimes lead to smaller advantage signals, which might slow down optimization a bit.
But they have a fix.
Yeah, they say this can be easily addressed by enlarging the learning rate, so it's manageable. Figure 8 shows this robustness quite clearly.
And does this improved exploration actually generalize? Does the model become better overall, or just on the specific types of problems it trained on with pass at K?
It generalizes. The paper states pass at K training shows stronger generalization ability than pass at 1 training. It improves performance not just on the training tasks in domain, but also on related but different tasks out of domain.
Where do they show that?
Table 1 has results on benchmarks like RCAGI, Enigmata, Corebench, even AIM math problems. Consistent gains across the board compared to pass at 1.
So the exploration skill it learns isn't narrow, it actually transfers. That's huge.
It really is. It means the model is learning a more fundamental reasoning or problem-solving capability.
Okay, let's get to the practical payoff. You mentioned earlier that pass at K helps pass at 1 performance in the long run. How does that work?
This is maybe the most compelling part.
Yeah.
The real magic happens when you do a 2-stage training process. First, train with pass at K to build up that exploration ability.
Get the model out of its local optimum rut, teach it to explore the solution space broadly.
Exactly. And then you follow up with standard pass at 1 training.
Why? To fine-tune it.
Precisely. To refine the now broader set of skills, to really hone its ability to find the best single answer quickly and efficiently. It's like pass at K broadens the search, and then pass at 1 sharpens the focus.
And the results of this combo.
Honestly, jaw-dropping. This is where they show that even the 7B model can surpass the powerful closed-source LLMs, including Grok 2, GPT-4o, and Claude 3.7 Sonnet on pass at 1 accuracy.
Wait, hang on. A 7 billion parameter open model after this pass at K, then pass at 1 training.
Outperforms massive, state-of-the-art closed models on their own preferred metric, pass at 1. Check table 2, specifically the P at KT plus P at 1T rows.
That's kind of incredible.
Yeah.
It implies those bigger models might also be stuck in local optima, or that smaller models have more raw potential than we thought.
Both could be true. Pass at K training seems to unleash the potential that was latent in the smaller model by improving its exploration, guiding it away from those suboptimal plateaus.
Is this benefit specific to certain models or tasks?
That's another really strong point. It seems remarkably universal.
How so?
They show it works across model size 7B and 32B models, saw boosts. Model architecture works for dense models like Quen and mixture of experts like Seed. Model family works for Quen models and Seed models.
And different types of problems.
Yep, natural language puzzles, multimodal reasoning like with images, complex math tasks, tables 2, 3, 5, 6, 7, they pile up the evidence across benchmarks.
Wow, so this isn't just a niche trick for one type of model or task. It's a potentially broad strategy for improving LLM reasoning.
It really looks that way. It makes high-performance reasoning potentially much more accessible, even with smaller open models.
Okay, stepping back a bit. They mentioned this idea of implicit reward design, building on the analytical derivations. What's that about?
It's a really forward-looking idea. They realized that by deriving those analytical formulas for the advantage values, they were essentially designing a reward mechanism implicitly through the math, rather than explicitly stating complex reward rules.
So instead of trying to write a complicated reward function, the structure of Pass at K itself, especially the analytical version, implies a sophisticated reward strategy.
Kind of, yeah. And they analyzed the shape of these implied rewards, or more accurately, the shape of the optimization strength, what they call eta, versus the model's current accuracy on a problem.
And what did that analysis reveal?
Two really cool things shown in Figure 9. First, Pass at K training naturally focuses on optimizing harder problems. Its peak optimization effort happens when the model is only getting things right about 25% of the time.
Whereas Pass at 1 peaks at 50% accuracy.
Right, so Pass at K automatically dials down the effort on problems the model already finds easy. This likely helps prevent overfitting on simple stuff and keeps the focus on areas where improvement is needed most.
Smart. What was the second thing?
The shape of the curve for Pass at K is asymmetric. It gradually reduces the optimization strength for very easy problems. Pass at 1's curve is symmetric, meaning it still puts considerable effort into problems the model almost always gets right.
So Pass at K is better at letting go of already mastered problems and focusing on the frontier, avoiding getting stuck polishing easy wins.
That seems to be the effect. It encourages continuous learning on the challenging examples.
And they even experimented with pushing this implicit design further.
They did. They tried things like exceeding Pass at K training, where they artificially shifted that optimization peak even earlier, focusing even more intensely on the hardest problems. Figure 18C.
Did it work?
It gave an initial boost to Pass at K performance, showing you can manipulate this curve, but they note it might slow down the eventual Pass at 1 convergence if you push it too far. It's a trade-off.
What else did they try?
Combination training. Dynamically mixing the advantage signals from Pass at 1 and Pass at K based on whether the model got the current problem right or wrong. Figure 12.
Adaptive rewards on the fly.
Sort of. And it showed really rapid improvements in both Pass at 1 and Pass at K scores. Best of both worlds, potentially.
And one more. Something about entropy.
Right, adaptive training based on policy entropy. This is really clever. They use the model's policy entropy, our measure of exploration, as a signal.
To decide how to train it.
Exactly. If entropy is high, model is exploring well, use the focused Pass at 1 advantage signal. If entropy drops low, model is getting stuck, playing it safe, switch to the exploration boosting Pass at K advantage signal.
Like a thermostat for exploration, adjusting the training style as needed.
That's a great analogy. And Figure 13 shows this adaptive approach leads to effective improvements in both Pass at 1 and Pass at K performance. It confirms entropy is a great indicator to guide the training dynamically.
So it's not just about choosing Pass at 1 or Pass at K, but potentially using the model's own state to adapt the learning process.
That seems to be a very promising direction. This implicit adaptive reward design could be a big deal.
Okay, let's wrap this up. We've gone deep into Pass at K training today.
We have. It's really a powerful technique, robust, efficient, and surprisingly effective for training large reasoning models.
And it's not just a simple trick. It's grounded in this fundamental rebalancing of exploration and exploitation, backed by analytical insights.
And even opens doors to these more advanced ideas, like adaptive implicit reward shaping.
The key takeaway for everyone listening has to be how it helps models escape those frustrating local optima enabling continuous improvement.
And leading to those stunning results where smaller models can challenge, even beat the giants after this training. It really unlocks potential.
Definitely a powerful tool to consider if you're working on pushing LLM reasoning forward.
Absolutely.
So, for our final provocative thought today, think about this shift. Moving from a one-size-fits-all training approach to one that adapts based on problem difficulty and the model's internal state of exploration. How could that core idea, tailoring the optimization process itself, be applied beyond just LLM reasoning? Could similar adaptive approaches help models in computer vision or robotics or scientific discovery continuously break through performance barriers in ways we haven't anticipated?
That's a fascinating question, taking this principle of adaptive state-aware optimization into other domains. Yeah, lots to think about there.
Well, hopefully this discussion gave you a solid understanding of PAS-K training and a potential roadmap for boosting your own work with LLMs.
Go forth and explore.